Section 1.1 is Patterns and Expressions. I can identify and describe patterns. Big ideas for this section. Some patterns can be represented using diagrams, words, numbers, or algebraic expressions. Variables can represent variable quantities in real-world situations and in patterns. In example 1 here, we're going to look at the figures, figure out what the pattern is, and then what the next shape would look like. So if we look here in figure 1, we have a triangle. Then in figure 2, we have a square. In figure 3, we have 5 sides of pentagon. In figure 4, we have 6 sides of hexagon. So it looks like every time we add a side, we started off with 3, then we went to 4, then we went to 5, then we went to 6. So the pattern here is that every time we're going to add a side. They're all regular polygons. All of our sides are the same, and it looks kind of wonky in like number 6, for example. But if you look in the book, they definitely, you can tell, all have the same side length. So they're regular figures, same sides, same angles. And the number of sides goes up by 1. So the pattern is side length, or sides, number of sides, plus 1. So the next shape, if we had 6, we add 1 to that. This one's going to be a 7-sided polygon. And I'm not even going to try and draw that in here, guys. But the next shape would be 7-sided regular polygon. So it's like if we split these up and put one more side in there. Okay, same sides, same angles, just 7 sides instead of 6. Now feel free to pause here and give this a try if you'd like. Look at the following figures from left to right. What's the pattern? And then show by drawing the next figure in the pattern. So if we look here, first we have a brown square in the middle and then 1 orange on each side. We kept the brown square in the middle and that first set of orange, and then we added another set of the orange. Now we kept our second figure and we added another set of orange. So if we look at this, we're probably going to, on our next figure, add 1 to each side, and it's going to be orange. Let's check. Yeah. So our pattern was that each time we added 1 orange one to all 4 sides, and we kept the figure before it. So we still have figure 1, then figure 2, then figure 3, and then figure 4. A mathematical quantity is anything that can be measured or counted. The value of the quantity is its measure or the number of items that are counted, and that's our value. So the quantity is anything that can be counted. The value is what you actually get when you count or measure. Quantities whose values do not change are called constants. They're constantly the same, they never change. Quantities whose values change or vary are called variable quantities. If they vary, they are variables. A variable is a symbol, usually a letter, that represents one or more numbers. Again, it doesn't have to be a letter here, guys. We could use smiley faces every time. But instead of introducing weird new shapes for us to try and figure out how to draw, they use things that are already common for us, things that we use every day, like X's and Y's. A numerical expression is a mathematical phrase that contains numbers and operation symbols. So 2 plus 3 minus 4, for example, is a numerical expression. It just has numbers and operation symbols. An algebraic expression, however, is a mathematical phrase that contains 1 or more variables. So if it has a variable in it at all, it's algebraic. If it's just numbers and symbols, it's numerical. In example 2, we're going to express a pattern with algebra using a table. And we want to know how many toothpicks are in the 4th figure. This is also on page 5 with a better drawing than I have up here, but this will work for now. So in our first figure, we have 1 figure and we have 4 sides. So we have 1 figure and each one of our squares has 4. In our figure 2, we have 2 squares and each square still has 4 sides. So we have a total of 8 toothpicks. Figure 3 has 3 big squares made from toothpicks, and each one of them has 4 sides. So we have 12. Now, that's pretty easy to figure out, but if we want to know our fourth figure, okay, we could pretend to add another square onto this side and count them up if we wanted. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So it's probably going to be 16 for 4. Or we could have said, well, on our fourth figure, we'll have 4 squares, and each square is going to have 4 toothpicks. And that gets me to my 16. Now, what is the expression that describes the number of toothpicks in the nth figure? So let's say we wanted to come up with an expression that would help us figure out any of them. We wanted the 20th, we wanted the 100th, we wanted the 62nd, okay? Rather than drawing out 67 little or 62 little squares, we can come up with a formula, with an expression. So if it was going to be 20, okay, we'd have the 20th figure is going to have 20 separate squares, and each square is going to have 4. So there we'd have 80. And it's the same idea if we don't know how many figure number. If we don't know how many squares there are, okay, we know that it's n. We've decided that it's this number, we just don't know what that number is. But we know that each one of those squares is going to have 4 toothpicks. So we can rewrite that as 4n. So the number of toothpicks in the nth figure is going to be 4 times the figure number, okay, because the figure number matches up with how many squares there are. So again, the 20th figure would have 80, the 4th figure would have 16, and the nth figure would have 4n toothpicks. We take 4 because each square has 4 toothpicks times n, and n is our figure number, which is also how many squares we have. Now, feel free to pause here and give this a try. We want to know how many tiles are in the 25th figure in this pattern, and we're going to use a table to solve. So something that's really helpful when you do these guys is to figure out what stays the same every time and what's changing. If it stays the same, it's our constant. If it changes, it varies. So if we look here, guys, it looks like every time it's a rectangle or a square, and it looks like every time we have exactly 1 brown. So I'm going to loop these two together as one thing, because every time we have one of those, that doesn't change. But the number of columns of just the orange ones do. So our process column here, we have 2 that stay the same every time, plus in our first figure we have 1 row of 2 oranges. So if we do that, we have 2 plus 2 is 4, and that matches how many we have here. If we look at our second one, again, our constants never change. They stay the same. That's always 2. Here, we have 2 rows of those 2 oranges. Sorry, 2 columns of 2. 2 times 2 is 4, plus 2 gives me 6. That matches. So for 3 here, again, I have the 2 that stay the same every time, my constants, and I have 3 columns of 2 oranges. 3 times 2, 6, plus 2, 8. Let's check it. 2, 4, 6, 8. Seems to work. So, to come up with a pattern that would work for any figure, we don't necessarily want to draw out the 25th figure. We sure could, but that's going to take some time and paper and pencil and work. So let's work a little smarter here instead of harder, or a little harder, smarter rather than harder. So we know that these 2 are going to stay the same every time. And we know that the number of orange columns we have seems to match our figure number. Here in figure 1 we had 1, in figure 2 we had 2, figure 3 we had 3. So if our figure is n, that probably means we have n columns of those 2 rows of orange. So we can rewrite this as 2n plus 2 for n figure number. And that works for anything. So if, for example, we want to find it for 25, we plug 25 in for our figure number, which was n. So 2 times 25 plus 2. 2 times 25 is 50 plus 2 gives me 52 tiles. And again, I have the same thing in this process column here. Oops. Okay, same thing here. We get to 52. Example 3 here is also on page 6. We're going to use a graph to determine our algebraic expression. You want to set up an aquarium and need to determine what size tank to buy. The graph shows tank sizes using a rule that relates the capacity of the tank to the combined length of the fish it can hold. Okay, so our combined length and then the capacity in gallons. If you want 5 2-inch platies, 4 1-inch guppies, and a 3-inch loach, what's the smallest capacity tank you can buy? 15, 20, or 25 gallon. I'm not actually sure that's how you say those. I don't know stuff about fish, but guppies I'm pretty confident in. So let's try and figure it out here. We want 5 2-inch platies. So in order to figure this out from our chart, our graph here, we need to know what the combined length of our fish is. So let's figure that part out first. We have 5 2-inch platies, so that's 10 inches. We have 4 1-inch guppies, and that's 4 inches. 4 times 1, 5 times 2. And a 3-inch loach, so that's just 1 times 3, which is 3. And to find our total, our combined length, we combine those and add them up. So we have 10 inches worth of platies, and 4 inches of guppies, and 3 inches of a loach, which gives us 17 total inches. So our combined length of fish is going to be 17 inches. But if we look here, 17 doesn't fit on our graph. We have 1, 2, 3, 4, 5, 6. Okay, so we're not going to get to 17. So we got to figure out what our pattern is. Well, if we look here, it looks like every time we go up 1 in inches, we go up 1 in gallons. Okay, so I went 1 more inch and I went 1 more gallon. 1 more inch and I went 1 more gallon. 1 more inch, 1 more gallon. That's our slope. But we start off with capacity of 2 gallons regardless. So for the combined amount of inches we have, it looks like we have to take that and add 2. So when it's 0, we add 2. 1, we add 2 to that and get 3. 2, we add 2 and get 4. 3, add 2, we get 5. 4, add 2, 6. So knowing that, we take 2 times our combined inches and add, we take our combined inches and add 2 to it. So our combined inches is 17 plus 2. We get 19 inches, and that's the minimum capacity tank we can get. But we don't have that option, so the smallest tank that we can buy is going to be a 20 gallon. Now feel free to pause here and give this a try if you'd like. The graph shows the total cost of platies at the aquarium shop. We want to know how much do 6 cost. So here we could fit 6 on our graph. We could just extend our graph and extend our pattern if we wanted. But that's not always going to work. 10 isn't going to fit on there. So we're going to have to come up with a plan. So it looks like 1 platy is $2. 2 is 4. 3 is 6. So we're going to take our number of platies times $2, or $2 each. So if I want to get 6, it's going to cost me $12. If I want to get 10, that's my number of platies, times 2, it's going to cost me $20. Okay, why is this graph points while the graph above was a line? Here we're talking number of platies. We're not going to go into a pet store and buy like 1.5 platies, right? But the inches could be half. We could have a 2.5 inch goldfish and a 3 3/4 inch platy. Okay, that's possible, but the number of platies has to be whole numbers. We're not going to buy 2 1/4 platies. So that's why we only have the dots here. But above, it could be any length, and that's why it's a line and continuous. Quick recap, some patterns can be represented using diagrams, words, numbers, or algebraic expressions. Variables can represent variable quantities in real-world situations and in patterns. And that's all.